Today we're going to look at our last chapter of Try 2, and we're going to be looking at exponential functions this chapter. This first question is an example of something that is growing exponentially or an exponential function. It says Sam is working in a biology class with a petri dish of bacteria. He estimates he has a colony of about 25 bacteria to start out with. Assuming the entire population of bacteria doubles every hour, find how much bacteria Sam will have after 5 hours. Why don't you try pausing this for a second, see if you can figure it out, and then check it in a second. So pause it, try it, and then we'll check and see what you got. Okay, let's see. One way to do this would be to make a table, and I'm guessing some of you maybe did that. At 0, or the start, we know there's 25. After 1 hour, 2 hours, 3 hours, we can figure out how many we have all the way up to 5 hours. So if it doubles after the first hour, now we're up to 50. If it doubles again, we're up to 100. Doubles again, 200, 400, and finally at 5 hours, we'd be up to 800 bacteria. And that is the answer for this one. That's how many it would be if it keeps doubling. This is an example where something doubles. This is an example of growing exponentially. You can see that at the start, we grew kind of slower. We grew by 25 after the first hour. The next hour, we grew by 50. The next hour, we grew by 100. And then we grew by 200. It starts off growing slow, and then it grows more and more and more each time. It gets bigger. This is, anytime you increase by a larger amount or a smaller amount each time, that's an example of an exponential. It's not growing by the same rate. This is one of the new functions we're going to be looking at. We've looked at a bunch of functions already. Some of the other ones we've worked with so far this year, linear. Back in Try 1, you guys looked at linear. That's y equals mx plus b equations. Typically with those, we're going to get one solution. It crosses the x-axis up to one time. Quadratics. We looked at these and Try 1 as well. ax squared plus bx plus c, those types of equations, and we can get up to 2 solutions. You got x squared, so you can get up to 2 solutions. Other ones we looked at other polynomial functions this trimester. This would be an example of a cubic function. It's going to have up to 3 solutions. This is one with x to the 4th. This one has up to 4 solutions. Crosses the x-axis 4 times. This last one's example, sum to the 5th power. Cross 1, 2, 3, 4, 5 times. Have 5 zeros or 5 solutions. Some other ones we looked at. Square root function. That's anything where you have a square root in the equation. And we looked at those ones. They're curved graph. We looked at some of the properties with the domain and range. We've also just got done talking about rational functions. Those are functions where you have some kind of expression on top and expression on bottom. It's a fraction basically, and because it's a fraction, this bottom function g, if it ever equals 0, we can't divide by 0. That's where we get things like asymptotes, where there's a line that our graph approaches but never touches. There's no value there. It's undefined at x equals 3. So those are some different functions we've looked at. This exponential one's the last type we're going to be looking at for the year. All right, what's some things then that we should know about exponential functions? Exponential functions are going to have this standard form listed here, y equals ab plus x. So things we'll talk about with this. The a, the first letter, that is your initial value or your starting amount. So it's your initial, it's what you begin with, it's the amount you start with. B in this equation is your multiplier. What are you increasing by? Are you doubling? Are you tripling? How much are you going up by each time? And then x, notice x is in the exponent here, that is why these ones are called exponential functions, because your variable's in the exponent. We could use this to solve a problem similar to like that first one we looked at with the Petri dish in the biology class. In that particular problem, our initial value, our starting amount, there was 25 bacteria. Our multiplier, we were doubling, so we were doubling each time. Our exponent in this case would be how many times that we doubled. We doubled 5 times because it was over 5 hours. If we solve that, we should get the same answer we got before of 800. Let's check just to make sure. So on the calculator, we should be able to do this problem. We would type in 25. Always use parentheses with these. 2, close the parentheses up, to the 5th power. So exponent 5. Hit enter, 800. So that's how you can solve that problem. Rather than making a table, you can use an exponential function to get the same type of result. All right, what we're going to do now is talk about some properties of exponential functions, some things you can know, and these are listed on your note sheet. Exponential functions are always continuous, which means you can trace them all without picking up your pencil at all. And they're also one-to-one, meaning for every x, there's a y value. Now, remember last chapter, we looked at functions that are not continuous. Ones that have asymptotes or holes are not continuous. These will always be continuous functions. Because of this, the domain, or your x's, is the set of all real numbers. You can put any x in for here, and we're not going to get any bad results. There's not going to be any division by 0 or square roots of negatives or all that kind of stuff we talked about that restricts the domain. The x-axis is an asymptote for these functions. And we'll see in a little bit, when you look at some of these graphs, you can see that your graph gets close but never touches. An example that you can see some of the graphs to the right there, this graph right here keeps getting closer and closer and closer to the x-axis but never actually touches. Same with this graph over here, keeps getting closer and closer and closer, never actually touches the x-axis. So there's a horizontal asymptote at the x-axis. The range is a set of all positive numbers where a is greater than 0 and all negative numbers where a is less than 0. So when you are looking at the equation, if this is a positive number, then your graph's going to be always above the x-axis. If this a number is negative, then your graph is going to be kind of below the x-axis the whole time. Some other things to note. The graph always contains the point 0a, or another way of saying that is your y-intercept is always whatever your a is. So this initial value is always going to be your y-intercept. Okay, notice down below here, we got a couple examples. This first one is y equals 2x. Since there's no number in front, we know it's kind of like a 1 there, or 1 times 2 to the x. So our initial value should be 1. And that means over on our graph here, you can see it crosses the y-axis at 1. 0, 1 is that point right there. Same thing on this other one over here. There's another example. This equation is y equals, there's no number, so it's a 1. And again, our graph crosses at the point 0, 1. So the a, whatever your a is your initial value. That's always a point where it crosses the y-axis. That one is one that you should know. That's an important property. All right, finally, the graphs of these functions are reflections across the y-axis. If you take a look at those two graphs, you can see they're just mirror images of one another. And that has to do with the fact that in this one, we have b, and in this one, it's the reciprocal of b. So therefore, they are reflections. All right. What we're going to do is take a look at a graph and see how we go about solving or looking to get the graph of a function. In this first one, we're going to sketch a graph y equals 3 times 2 to the x power. One thing we know right off the bat is our initial value is 3. Since that's our initial value, we just got done talking about whatever that number is, that's where it crosses the y-axis. So we know right here where we have 0, our y value is going to be 3. So over here on our graph, we know this is a point, 0, 3. That's where our graph's going to cross. Now to get the other functions, we could do a couple things. One, we could look at the multiplier. On this one, our multiplier is 2, which means we're doubling each time. So if we doubled from 3, we would get 6. If we double 6, we're going to get 12. If we're going the other way, we have to think what was being doubled to get the value in front of it. So what value is being doubled to get 3? 1.5. And we could work backwards from that. Another thing we could do is use your calculator. You can use your calculator in a couple of ways. One would be to just actually plug the number in. So for example, if you want to figure out what it is at -2, you could do 3 times 2 to the power of -2, enter it in your calculator like that, and you can see it's 0.75. Another thing you could do is graph it and just pull up the table like we've done with some of the other graphs. So to graph it, remember, go to your y equals, type in the function, 3 parentheses, 2 to the power, and here's where you put your variable x. It's an exponential function. Hit graph, you can see what it looks like, and then if you hit second graph, you can see the table. So scrolling up here, we can see the values. For -3, it's going to be about 0.375. Now it's just a matter of going over to the graph and plotting the points out. We have a point at 1, 6. 212 is kind of off our graph. We'll leave that one. -1, 1.5, 2. And you kind of estimate, and you can see we get that exponential shape. It starts off growing slow, but as we get up here, it's growing very rapidly. There's another one on your sheet there. Let's take a look at this one. We can do the same thing. Again, let's look at some of the key things we know. Our first value there, that's our initial value. So we know at 0, it's going to be 2. Also on our graph, we know it crosses at the point 0, 2. Our multiplier on this one is 1/2. So if we multiply by 1/2, we'll get the next value. Half of 2 is going to be 1. Half of 1 is 0.5 or 1/2. Going back the other way then, kind of the same thing. What was being half to get this value to? 4 was. What was being half before that? 8 and 16. And again, you can pull up the same values using the table on your calculator as well. And now we go through and graph those points. We can see what it looks like. There's a point at 1, 1, 2.5, -1, 4, -2, 8. -316 is kind of off our graph. This one is decreasing. This one is an example where it decreases rapidly. We call that exponential decay. And we're going to talk a little bit more about exponential growth like we had on the last problem in exponential decay tomorrow. So for tomorrow, we'll continue looking at exponential functions.